Far beyond the warmth of the sun, past the vast luminous rings of Saturn, drifts a small, unassuming moon whose brilliance belies the secrets it conceals. Enceladus, scarcely 500 kilometers in diameter, shines like a jewel against the darkness, reflecting nearly all the sunlight that strikes its icy surface. Its albedo, one of the highest of any known body in the solar system, makes it appear as a perfect sphere of frozen white, an oasis of ice in the void. For decades, it was merely one of Saturn's hundreds of moons, catalogued, studied only by telescopic observation, and largely considered inert, a minor satellite orbiting a gas giant with majesty but no mystery. Yet, appearances in the cosmos are often deceptive. Beneath its icy exterior lies a dynamic and extraordinary world, a planet-like environment that challenges our most fundamental understanding of habitability and the prerequisites for life. The story of Enceladus took a dramatic turn with the arrival of the Cassini spacecraft in the Saturnian system in 2004. Cassini was a marvel of human engineering, a robotic probe equipped with spectrometers, magnetometers, imaging systems, and mass analyzers designed to explore Saturn and its diverse moons in unprecedented detail. Among the moons of Saturn, Enceladus seemed, at first, unremarkable, a small body orbiting in relative isolation. But during its multiple flybys, Cassini detected a phenomenon that would redefine the moon's significance and, by extension, the search for extraterrestrial life. Towering plumes of vapor erupted from fractures in the southern polar region, rising hundreds of kilometers above the surface. These features, later named tiger stripes for their linear appearance, were not mere outgassing events as seen on other icy bodies. They were sustained, energetic plumes, ejecting material from beneath the crust in quantities sufficient to form a faint, continuous halo of material around the moon. The detection of these plumes initiated a cascade of scientific inquiry. Cassini's instruments, flying repeatedly through the vapor, analyzed the composition of the ejected material and revealed a mixture of water vapor, molecular hydrogen, methane, carbon dioxide, nitrogen compounds, and a suite of complex organic molecules. The presence of water and molecular hydrogen alone was revolutionary, implying not only the existence of a liquid reservoir beneath the ice, but also active geochemical processes capable of producing chemical disequilibria, conditions essential for the emergence of life. Molecular hydrogen is a highly reduced species, a potential energy source for microbial metabolisms analogous to those found on Earth's hydrothermal vent systems, and its presence suggested that serpentinization reactions were occurring at the interface between the rocky core and the overlying liquid ocean. Subsequent analysis of the plumes confirmed the presence of salt and silicate particles, providing compelling evidence that the ocean beneath Enceladus's ice is in direct contact with its rocky core. This configuration, a global water layer overlying a differentiated silicate interior, establishes the fundamental preconditions for hydrothermal activity. Tidal flexing, generated by the gravitational interplay between Saturn, Enceladus, and neighboring moons, continuously deforms the interior, producing frictional heating sufficient to maintain liquid water at depth despite the ambient surface temperatures approaching absolute zero. This internal heat flux allows Enceladus to maintain a subsurface ocean in a thermodynamically stable state, enabling water-rock interactions that drive hydrothermal circulation and generate chemical gradients, which in turn can serve as metabolic energy sources. The physical characteristics of the ocean itself are now reasonably well constrained. Modeling of the gravity field, topography, and ice thickness suggests an average ocean depth of tens of kilometers, potentially reaching a global volume exceeding that of all terrestrial oceans combined. The overlying ice shell, measured at approximately 20-25 kilometers thick at the poles and thicker at mid-latitudes, acts as both a protective barrier and a thermal insulator, stabilizing the liquid layer and preventing rapid freezing despite the harsh radiative environment of Saturn's orbit. Beneath the ice, the ocean is likely stratified, with density gradients controlled by temperature, salinity, and the concentration of dissolved ions. These gradients, combined with convective processes driven by tidal heating and chemical interactions with the silicate core, produce a dynamic environment capable of sustaining complex geochemical cycles over geological timescales. Cassini's observations of plume particle sizes and velocities also provided indirect evidence for the ocean's properties. Ice grains containing salts and silica nanoparticles suggest high-temperature hydrothermal venting on the seafloor, with localized temperatures exceeding 90 degrees Celsius, sufficient to dissolve silicate minerals and produce fine particulates that are later ejected through the fractures. The detection of both micron-scale silica particles and nanoscale silica clusters indicates a range of hydrothermal activity intensity, implying heterogeneous venting sites and variable chemical conditions, which could support diverse prebiotic chemistry. From a geophysical perspective, Enceladus exemplifies a tidally heated ocean world. The mechanics of tidal flexure generate cyclical stresses in the ice shell and mantle, producing fissures and fractures that act as conduits for oceanic material to reach the surface. These fractures, aligned with the south polar tiger stripes, serve as direct windows into the subsurface environment. The continual activity of the plumes demonstrates that the ocean is not a static reservoir, but a dynamic system with material being exchanged between the core, ocean, and surface over timescales relevant to chemical evolution. Chemical analysis of the plumes has revealed the presence of complex organic compounds, including long-chain hydrocarbons, nitrogen-bearing organics, and oxygenated species. These molecules represent prebiotic building blocks that, under the right conditions, can polymerize to form amino acids, nucleotides, and lipid-like compounds. The detection of phosphate salts in the plume ejecta is particularly significant, as phosphorus is a limiting reagent in terrestrial biochemistry and is essential for energy transfer in the form of ATP. The presence of all major biogenic elements, carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus, establishes Enceladus as one of the most chemically complete habitats for potential life in the solar system. Isotopic measurements of hydrogen and carbon ratios provide further evidence for active chemical processing. Variations in deuterium to hydrogen ratios suggest fractionation processes consistent with hydrothermal circulation, while carbon isotope ratios indicate that methane production may be driven in part by abiotic serpentinization reactions, producing a chemical energy source potentially exploitable by microbial metabolisms. The interplay of tidal heating, chemical gradients, and organic availability creates a plausible pathway for life to originate and persist in an environment entirely independent of solar irradiation, relying instead on chemolithotrophic energy sources. The implications of these findings extend beyond the confines of the Saturnian system. Enceladus demonstrates that habitability is not restricted to the circumstellar habitable zone, but can arise wherever liquid water, chemical disequilibria, and essential elements coexist. This revelation has transformed the paradigm of astrobiology, positioning icy moons as prime targets for the search for extraterrestrial life. The combination of a global ocean, sustained hydrothermal activity, and the presence of complex organics constitutes a natural laboratory for prebiotic chemistry and potentially extant biology, preserved beneath an insulating shell of ice.